Thank you, Andrea. So today we have the honor to host Professor Bertozzi, and I will present her, even if we all know her outstanding career. Andrea Luis Bertozzi is an American mathematician, and she's working generally on nonlinear PDEs, but she works on all the aspects of applied mathematics, maybe. And she obtained a PhD in Princeton University, discussing a thesis on existence, uniqueness, and characterization of solutions to the contour dynamics equation. And then she joined UCLA in 2003. But before, she has been a Dickinson instructor at the University of Chicago, and then professor of mathematics and physics at the Duke University. She won several prizes, several important prizes. I will mention some of them. She is fellow of the American Mathematical Society and of the American Physical Society. She is also Science Fellow since 2010, and in 2019 she was awarded of the Siam Kleinman Prize. Her research activity touches, as I said, many disciplines connected with applied mathematics, and furthermore, she recently concentrated on the ongoing pandemic. So that's why we invite her to give a talk on this cycle of seminars. So it is a great honor to leave the stage to Professor Bertozzi. So now the stage is yours.
Thank you very much. Yeah, thank you so much. It's a pleasure to be here on Zoom. Of course, being in person would be better, but Zoom is wonderful. And it's been a great communication platform, frankly, to be able to talk to people all over the world. So, for example, in the spring, soon after the pandemic started, I was scheduled to teach a graduate course on fluid dynamics with my colleague, Marcus Roper, who's also a math biologist. And we talked to each other and we said, you know, we should really teach a class on pandemics. And we gave ourselves a crash course on pandemics, and we taught a graduate seminar that was attended by researchers, not just from UCLA, but from all over the world. We had people coming to listen to us from France, from Germany, from the UK, from Hawaii, and from several other universities in the United States. So that was I think we all felt like we had to do something, to contribute. And so one of the things I did was I started some research myself in this area. And we had quite a lot of students working with us in the summer of 2020. The US National Science Foundation actually gave us a small grant at UCLA, and they also sent some students who were supposed to be working in the national labs, but they were closed because of COVID, and the National Science Foundation asked me if I could take on several additional students beyond my own group and beyond our summer program, because these students were planning on doing research at the national labs and they weren't able to go. So we included those students in our summer program. I'm going to speak today about some research that came out of that, and also just research that that we've been doing at UCLA. So thank you very much. So let's see, I'm going to go into full screen mode here. So hopefully you all can see this. Great. Okay. And I just closed my chat box, so please interrupt me if somebody has a question. So I think we'll just be sort of informal today. Okay, great. So I guess I can also mention that, one of the reasons why I was so concerned about COVID was that I had a younger sister who was working in a nursing home in New Jersey, skilled nursing facility with elderly patients, and she saw 20% of the patients die in 1 month because of COVID. And she herself got the disease. Everybody got it at the nursing home because they were not having enough PPE, and they were just, basically It was early in the pandemic when both New York and New Jersey had quite an upsurge in infections. I have elderly parents who were alone on the East Coast. So it was a kind of a scary time. So here we are now, you know, almost a year and a half later. My whole family is vaccinated. None of us died, which is great. But you know, it's taken a toll on the world, this disease. So so my research actually started very early on, and it was I started getting interested in epidemics quite early on. I would say in February, late January, early February, when I heard about the spread of this disease, and I started reading some news articles. And I started running my own simulations. You know, it's very easy to simulate an SEIR model. You can do it in an Excel spreadsheet. You don't even need MATLAB to do that. It's incredibly easy. And the world saw the impact of science and modeling quite early on, because on March 16, there's a famous group at Imperial College in the UK, and they released this report where they had simulations, and they basically said, you know, these are not predictions, but they're what we call counterfactual simulations based on the estimated spread of the disease, the rate of the spread of the disease. And they were predicting that if nothing changed, if everyone kept on going about their basic lives without any changes in behavior, that the United States would see over 2 million deaths, and Great Britain would see over 500,000 deaths. And that report came out on March 16. And that report was highly influential in shutting down both the US and the UK. We, of course, were watching what was going on earlier in China, in Italy, because we know Italy was very badly affected early on in the pandemic. And so we were looking at those numbers. Spain was also hit pretty hard. And I think between a combination of the you know, large number of people being affected in several countries early on, and these predictions, you know, common sense suggested that maybe a shutdown was a good idea. But nevertheless, it was kind of hard to predict. And I think this study has gotten a lot of criticism from the public, because the number of deaths in this graph never actually happened. That said, the United States has seen maybe 1/4 of this number of deaths. So it's still the same order of magnitude. And we all know that our lives have changed drastically. And it's because of that change that we haven't seen, you know, the 2 million deaths. So it's sort of interesting to think about what happened early on, how the role of science, and sort of where we are now. Also, it's kind of hard to explain, to the public, I think. I'm having a little trouble with my scrolling here. It's a little hard to explain to them the role of counterfactual studies compared to forecasts, right? And that was not a forecast, it was really a counterfactual study. Another thing that we saw early on was the disparities in outcomes as a function of age, right? As a function of something as simple as the age of the person who got the disease, right? So we saw that in the very young population, the hospitalization rates were relatively low, and the infection fatality rates were quite small. But nevertheless, some people were still being affected. So, for example, in this 20 to 29 population, it was estimated to be 0.03% fatality rate. However, I know of somebody who was a student at UCLA who died of COVID-19 early on in the pandemic in his early 20s, right? So there were definitely healthy people who were being hit. One of the issues, of course, was that at the early stages, the hospitals didn't really know how best to treat the disease because it was new. Okay, so, you know, I was quite interested in how mathematicians can play a role. I happened to be posting some of my simulations on Facebook, and I have a lot of science friends on Facebook, and those friends included George Moeller, who's a computer scientist at IUPUI. I met Elisa Franco on Facebook. She's actually at UCLA in mechanical and aerospace engineering. Martin Short is at Georgia Tech. And Daniel Sledge, who I met through this group, is a political scientist in Texas. And we started corresponding over the internet and comparing the modeling that we were looking at. And somehow organically, we developed a research paper, which has since been published in PNAS in 2020. And the goal, of course, at such an early point in time was to try to understand the early time dynamics in the United States, because that's where we were living, and using very parsimonious models. So this is one of the issues that comes up with epidemiologists, because there are kind of two ways of thinking about this. A very skilled scientist who's an expert in the biological and medical sciences might prefer a model with a fairly large number of parameters that you can measure and estimate from field data and from individual patient accounts, right? The other way of thinking about this is that with early time data, there may not be a lot of data, and it might be better to use what we call a parsimonious model, where you don't have a lot of parameters. And so that was what we looked at with parsimonious models. With a small amount of data at the early stages, fewer parameters might be better to fitting early time data. And we have now a quantitative way of showing that. So I'll explain that. It uses something called the Akaki information criteria, which is a well-known statistical method that can be used to compare models, especially models with different numbers of parameters. We also, in addition to looking at the classic compartmental models of SIR and SCIR, we also looked at a self-exciting point process model, which is a statistical model. So, and I see this slide is old, so next week I think was from my class, so we'll hear about it today. Right, so Elisa, who is from Italy, was doing a lot of simulations of the exponential growth. And she, coming from Europe, she was quite interested in estimating things like the reproductive number in different countries, and just generally speaking, estimating exponential growth. And so, a simple way to see that is to take the data. So, if something's increasing dramatically, it's hard to tell from a plot like this, whether it's exponential growth or whether it's like just a parabola, growing like a polynomial. But if you put it on a log linear plot, right, and then you look for straight lines, that would be your exponential growth. So that's a very simple method to do. We did some estimations early on, or I should say Elisa did this work, and found that the doubling time estimates were actually smaller than early estimates that were collected in Wuhan from a group that published in the New England Journal of Medicine very, very early on, because Wuhan, of course, was the original epicenter of the outbreak. Okay, so one of the things that we also looked at from a modeling standpoint was the role of transmission rate versus recovery rate. So if you're looking at kind of the standard compartmental model, you have a transmission rate and you have a recovery rate. However, if you look at the dynamics at very early times, there's a delay before patients actually start to recover. And so very early on, the exponential growth is driven primarily by the transmission rate, which gives you a larger exponential rate. If you're looking for something that's e to the alpha t, the alpha is early on will not involve the like very early stages. You won't see the effect of the recovery but at later stages, but still not at the peak of the pandemic. So you're still looking at early time dynamics. That rate decreases to beta minus gamma because of the fact that some fraction of your population is also recovering. So that's so that was just a simple model analysis early time. So this is just a review of the compartmental models, which probably don't need a lot of discussion for this audience. These are 100-year-old models that basically look at full mixture of the population. So you imagine a larger population, and the population is interacting in a sort of a very full mixed state, and you have a transmission. So everybody starts in a susceptible compartment with maybe just a small number of infected individuals. So in a novel pandemic, at the very beginning of the pandemic, basically there's probably one, maybe a couple if like they got infected at the same time, but we're talking about essentially one individual who then makes the whole world sick, which is kind of crazy, but that's how it works. And it's because everyone else is in the susceptible category, and the transmission rate is so there's some constant beta that's disease dependent and depends on the contact structure of a person coming into contact with another person. Epidemics have a very simple mechanistic way of spread, right? You literally need an infected person to come into contact with a susceptible person, and that's how the disease is spread. So it's very simple, and it's very easy to model mathematically because of the simple mechanism. Right, so, but on the other hand, things like physical distancing will affect this parameter beta. And then S is the susceptible population, the number of susceptibles, and I is the number of infectious. So you have the product of these two that gives you a rate of transmission from susceptible to infectious. And then the infectious population has a recovery that does not involve anybody interacting with anybody else. You recover on your own. So that's a linear function of the infectious population with the rate gamma. So beta and gamma both have timescales, right? They're basically like 1 over time. And then you have a recovered population, and you can think about this model either as a stochastic model as an individual based stochastic model, or you can look at the mean field continuum limit, and that the mean field continuum limit has to make a couple of assumptions. One is that your population is fairly large. If you only have 10 people, you're not going to see beautiful smooth graphs like this. And in fact, even with several thousand people, you still won't see this, right? And I'm going to show you some examples and ways of estimating finite size effects. But in a large population with a lot of individuals and full mixture, right? So everybody's interacting with everyone else. To leading order, we get this kind of simple ODE dynamics. And I think for this audience, I'm imagining most of you are familiar with the SIR model. So perhaps the number that everyone is familiar with is the reproductive number, R naught. For the SIR model, that's a dimensionless number. And we get it by taking these dimensional equations. We normalize them with the total population so that we end up looking at percentages rather than units of numbers of people. So that's why we see 1 over n here. And then you can also rescale the S and the I and the R by n. And the other thing you do is you divide all of these equations by gamma, right? Because beta and gamma are both rate constants. So beta over gamma is dimensionless, right? So you divide by gamma, and then that gives you an R naught here, an R naught here, and a 1 over here. So R naught is a dimensionless reproductive number. And that's the number that we're all interested in terms of the disease becoming an epidemic. If you can somehow get your population under control so that R naught is less than 1, then you will not have an increase in the spread of disease. Okay, the other thing we see is that in the long time limit, your infectious population, well, it increases and it decreases, but it doesn't, so this decays, so the infected population decays to 0, but the susceptible population and the recovered population do not asymptote to 0 and 1. They do not. They asymptote to some constant, and that constant depends upon the reproductive number. So at the end of an epidemic, there will still be susceptible, even with the simple SIR model, there's always susceptible people left in your population. Okay, yeah, so then you have some basic conservation. So you have conservation of the total number of people, unless you include mortality, right, in this dynamics. And we don't have mortality in these equations, but you can put that in there. Or you can just assume that some fraction of the quote unquote recovered people are actually dead, which is not a pleasant thought, but it is true in the case of COVID-19. You can write down a lot of very interesting results. So for example, if you have an uncontrolled epidemic, there's a formula for, it's an implicit formula for the size of the susceptible population and the recovered population in the time to infinity limit that involves something called the Lambert W function. But basically you can write down a formula for this in terms of the initial data. So that's interesting. And one of the comments I wanted to make is that the size of the population when you have an uncontrolled pandemic is not like at the end of that pandemic, the number of people who are recovered, who basically are immune, is typically larger than the minimal percentage required for what we call herd immunity. So that's another thing that you can look at. So in the case of trying to design vaccines, for example, if you can suddenly vaccinate your population up to a certain percentage, which is the minimum required for herd immunity, that will typically be a lower number than these numbers that you get here. All right, so you can look at some phase diagrams just to see how how the epidemic behaves. So a simple calculation with the ODEs allows us to see that if we plot SI on this axis, percentage infected and percentage susceptible on the horizontal axis, you can draw curves that just describe the entire pandemic, right? So time is not on here, but you can see, for example, that the maximum number of infected individuals at a fixed time is a number that actually has a very simple formula. It's 1 over R naught. And these are some of the plots that we get. So the peak of the number of infections happens when the percent susceptible is 1 over R naught. For even moderate size R naught bigger than 1, this means that a fairly large fraction of the population will have been exposed and infected at the peak. And at the end of the epidemic, the percent unaffected with a modest size R naught. Like, so for example, we were seeing estimates of like in California, I'll show you in a slide coming up, that we were estimating the R naught early on to be, somewhere in the 2 to 3 range. And that's already pretty large, meaning that if the epidemic had gone uncontrolled in California, a large fraction of the population would have been infected, and then some fraction of those people would have died. And so that would have been quite a lot of deaths. Okay, so I mean, here's an example. This is from an old paper before COVID-19. It was published in 2007, Bootsma and Ferguson. I like these plots very much because they show us with a simple SIR model what can happen in terms of distancing controls, right? So this plot shows the proportion of the population that eventually is infected. The blue line is as a function of R naught. It's for the uncontrolled epidemic, and the red line is the minimum needed for herd immunity. And you can see, for example, for R naught equals 2, which we're going to look at an example on the right hand side. For R naught equals 2, the herd immunity, the minimum required for herd immunity is only 50% of the population. But if you let the epidemic go uncontrolled, you get an 80% percentage of the population that actually gets the infection. So that's a pretty big difference. That's a difference of 30%. We also see that if you're going to introduce some kind of distancing measures to control the spread of the disease, having too effective a control, meaning that so too effective is a little bit relative here. This is making a lot of assumptions, right? So we're assuming here that the only way that you can get out of this is to have the disease spread through the population, which of course is not the only way if you can develop vaccines. But nevertheless, what we see here is that if you have a lot of control, which is the red line, the problem with this red line is that you have a much smaller outbreak than the uncontrolled case. But then let's say that at week 11, you decide that you're going to open up everything and let people go back to their normal behavior patterns. What you'll see in that case, sorry, my mouse likes to have a mind of its own. So what you'll see is a second outbreak. And we've seen this all over the world, right, with COVID-19. Whereas there is sort of an optimal rate that you can control things so that you don't get a second outbreak. But of course, the initial outbreak will be larger. So you have this trade-off between the possibility of having more outbreaks later on versus reaching herd immunity. So, and that can be understood with very simple combination of simulations and analysis. Okay, so what did we do? We decided to look at the dimension, like completely non-dimensionalize the SIR model, because the literature on epidemiology typically does not do this. But from the standpoint, like I'm somebody who is, started my career modeling physics problems rather than medical problems. And I thought it would be interesting just to see, because we're looking at a pandemic that's hitting the entire world, right? And so you can compare and contrast outbreaks in different parts of the world by trying to look at like a completely dimensionless rescaling of a simple model. So if we look at the completely dimensionless SIR model, that means that we have a dimensionless time as well as dimensionless S, I, and R compartments and the dimensionless reproductive number, right? So the dimensionless time is just a rescaled time, which is gamma, which is the recovery rate times T, right? And since gamma has units of 1/T, tau is a dimensionless time. So what you see when you do this rescaling, if you take any solution of the SIR model, with a sufficiently small initial infected rate, all of these solutions basically collapse onto one set of curves. And so how do we see that? Well, there's basically two ways to control the collapse. One is you just dimensionalize everything. The other thing is that you have one thing to fit, and that one thing to fit is the initial percentage of the infected population. And that number gives you the time to the peak infections, which is the distance from time, whatever time 0 is, to the time of the peak infections. And so we can see how this works by looking at several simulations with different orders of magnitude of your initial infection rate, right? And so this would say correspond to different size cities, right? If you think about like in the real world, what does this correspond to? But let's say that you introduce the virus with just a few people in each city, but the cities have different population sizes. So in the dimensionless world, you're going to be rescaling to the fraction of the population, which means that you'll have different fractions of the initial infection rate. And it's very beautiful. What you can see here is that if we look at these different curves, we'll see that they're basically almost exactly translations of each other. Not 100%, but so close that these curves basically collapse onto each other. And you can look at the time to the peak infection as a function of the initial infected percentage, which we call epsilon. And you can see that it very nicely depends logarithmically on epsilon. That's indicative of that exponential growth in early times, right? So it's kind of pretty that you get this very simple dimensionless model that we can draw on it at later points when we're looking at different effects of controls and things like that. Okay, so that's a dimensional. So also as an educator, if you're ever teaching students about dimensionless scaling of differential equations, I think this is a nice example. It's much easier than the Navier-Stokes equation, right? Which is harder. This is just an ODE, and it has basically just two dimensionless parameters here. One is the reproductive number, and one is this time rescaling and the time shift. Okay, so what does the similarity solution tell us? It tells us the transmission rate we know the transmission rate depends on the physiology of the virus and social distancing measures, but the recovery rate depends only on the population demographics and physiology of the virus, but not distancing measures. Of course, medical interventions could also affect the recovery rate. R0, the ratio of these two things depends on social distancing. The time scale of the ramp up and peak depend on gamma, which is largely independent of social distancing. So that's another detail there. And the final state of the epidemic depends only on R0, but not on gamma. At least, well, I mean, it depends on gamma, and that R0 includes gamma, right? But if you were able to look at, you know, different groups where R0 is the same, gamma changes, you would see the final state of the epidemic the same in both of those. So two cities with the same R0 should see similar behavior of the virus as a function of the total population density, but with a possible shift in time. So the larger city would see that peak of the outbreak happen later, just because they have more people. Okay, so here's an example. So these are counterfactual. Did not actually happen. But you know, in March, when we were running our simulations, California managed to shut down pretty early. I remember that so as somebody living through this, I remember watching the news, and we were seeing the initial outbreaks in New York. And I thought New York was just, you know, they were not going to be able to shut down soon enough to really control the epidemic early on. We all kind of knew this, and Governor Cuomo even decided to wait longer than California waited. So California went into the shutdown very fast. There was a Monday when we were speculating if UCLA was going to move to online classes. By Thursday, they just said online classes, everybody, like now, right? So they just told us, don't even come in. And by that weekend, like by Friday, which is like the next day, the entire state of California shut down. It was like that. At the same time, Governor Cuomo in New York was telling the population that he was going to give them the weekend to get ready for a shutdown. And I was sort of having an exploding head in California, because I knew that this was going to cost lives in New York if they did that, but that's what they did. So early on, California was able to really control the epidemic. And, you know, our president, Donald Trump, was speculating that maybe we could open on Easter. And, you know, of course, those of us running simulations were like, no, you cannot open on Easter. We decided for our paper that we would pick we were looking at Easter as an opening date. We thought, yeah, no, let's not do that. That's too soon. But, you know, California has a holiday on, well, it's not an official holiday, but there's May 5th is Cinco de Mayo, which, you know, a lot of people celebrate in Los Angeles. So we thought, well, okay, let's suppose that everything opens up on Cinco de Mayo. Let's see, hold on. Let me go back. Oops, there we go. Yep. All right, so we were looking at a couple of different scenarios here. Yes, so we were looking at actually these are two different reopening dates. So basically, you can open slightly earlier, you can open slightly later, and here's what you see. What you see is that if you open slightly earlier, well, of course, you're going to get the same epidemic that you would have had if you had not closed at all. It's just going to be shifted in time. And because the initial infection rates were fairly small in California, you can see that if you open at a later, even a later time, it's still just literally a shift of the entire epidemic. This is the infected population. We were using an R0 of 2.7 for the state of California, and this was just a simple SIR model, and I'll explain why we chose that one in a bit. Here's a contrast to New York State, right? So this is New York State if they did not close at all, right? And of course that never happened, it's counterfactual. This is also counterfactual, but it's a little closer. So this is with the shutdown happening when it actually did for New York State. And then we looked at what happens if they reopen on May 5th, and you can see a change. You can see a change in the derivative, right, of this graph at that point in time. But notice that the outbreak that you get in the second scenario is not as large as the uncontrolled outbreak, right? They're quite different, and that's because you already have a lot of infected people. In fact, you can see we're close to about 20% infected there, and we can go back and look at the serology studies that were done for New York City in particular. And the serology study, that's measuring antibodies, right? So they did some actual field tests of people in New York City and found that on the order of 20% of the population of New York City actually had gotten COVID-19 sometime in April. So very interesting that such a simple model, although it's not, it's certainly not exact, it certainly gives you a flavor of what actually really happened in the population. New York City, I think, would be a good example of a population for which a full mixture model would make sense. Okay, so that's just some early time discussions. I think I don't want to take too long, so I think I'm going to skip this slide. I want to mention that, of course, there's a more complicated model called the SEIR model that includes the exposed population. That's basically when you have a delay between getting exposed and actually becoming infectious. And we know for COVID, that's on the order of 5 to 10 days, right? I mean, I think it averages around 5 to 6 days, but for some people it takes longer. So that's an important, that adds another parameter to your model, because you're going to have this parameter A, which basically takes you from the exposed population into the infected population. So it adds another parameter, which is important. Okay, so historical data. So the 1918 pandemic, which was the one that was the most recent one since COVID-19, happened 100 years ago. There's a lovely paper that was published in 2007 by Bootsma and Ferguson, where they actually fit field data from the United States to an SEIR model. And I thought that was quite interesting, because what it does is it gives you an idea of what might have happened. It's a nice counterfactual to give you an idea of what might have happened had they not gone into shutdown in the various cities in the United States in 1918. It also gives you an idea of the role of the distancing measures, because we have all of that data actually from over 100 years ago. What they did was they had a transmission rate with controls, so the controls are here, but they also had a reactive component, which is from the mortality, right? So this is deaths. So basically, you can decide not to go out and meet other people because the government is telling you you have to stay home, or you can stay home because you see a lot of people dying and you are smart enough to know that maybe you shouldn't go out. Okay, so those were the two effects that they looked at. And they ran a bunch of different models and compared it to 16 cities in the United States. And they had to make some choices as to which model was the best. This particular, so they're all sort of the same model with different choices, like do they have the R0 depending on the city, so they chose an R0 that was common to all cities. Do they have the per capita death rate depending on cities, they made that dependent on cities, et cetera, et cetera. And what you can see is that I love this graph, right? Especially during the early time of COVID-19, it was very interesting to look at this historical data for the different cities in the United States. So what we see is a green line. So the green line for the Bootsma-Ferguson paper is basically telling us what might have, that's the counterfactual, right? So the X's, the blue X's are the actual deaths, and the green line is the counterfactual for what they believe would have happened had there been no shutdown, right? So you can see Kansas City, for example, would have had a marked difference between the actual deaths and in the case of actual deaths versus no shutdown. You can see the effect of maybe too short a control and maybe too strong a control at early time. So they open up and then they have a second outbreak, and then they had a second. So the light green bars, this is time, this is the total number of deaths. The light green bars are telling us the time period for which they actually initiated controls, right? That's what that's telling us, where the government said, you're not going to go out, right? Philadelphia, this is a famous one. Philadelphia actually had a parade scheduled, and they decided not to cancel the parade. And they started the distancing measures for a short amount of time, but they waited a long time. And you can see that the actual deaths were very close to the sort of worst case scenario, which is unfortunate for Philadelphia. Whereas in other cities like San Francisco, where they closed down earlier, they had a big difference between the potential mortality count, what actually happened, but again, a second wave, right? So very interesting to look at this historical data with SEIR. In my opinion, SEIR makes a lot of sense with historical data because you have a full data set. It's not like early time where you have just a limited number of data to look at. Okay, I have a lot to say, so I think I'm going to skip this slide. So in our paper, we were looking at much earlier time data. So one of the things that we were interested in doing was looking at a model that makes sense for small number counts. And so you're actually looking at individual based models. So you could go to a full individual based model where you have separate, processes, stochastic processes to model the infection and the recovery. We did not do that. We chose to look at a Hawkes process where there's one process, but it includes the infection and the recovery. So basically what the Hawkes process is, it's like this. So you have, this is the rate of events, gamma. And in this particular model, this is early time. So we're looking just at infections. So you have the dynamic rate of events, lambda, and lambda has a background Poisson arrival process. So these are people showing up in your city with COVID-19. So that's what that is. And then you have the rate of spread between people in the population. And this is the excitation. So this is, we're assuming a dynamic reproductive number that you can try to estimate. And then this is the event, these are the self-excitation. So this is basically one sick person infecting another sick person. And there's a time difference here, right? So this W is drawn from some probability distribution. We chose a Weibull distribution that includes the incubation time for exposure. So the exposed population dynamics is included in this parameter here. And with that, you can actually estimate dynamic reproductive numbers. So for example, here's China. You can see starting out with about 3 and of course decaying over a 2-month period. You can see, and this is like when they went into lockdown here, but you can see Italy here, that's your country, right? Again, far above 1, so reproductive number. So this is, so you have some, the estimate of course has some variance here, but we're seeing averages close to 2 at the initial outbreak. And then of course the United States was time lagged, right? Because we shut down a lot of air traffic into the United States. So that got us a little bit of a time lag, but still we had a big increase, right? And then on April 1st, we were estimating both New York, Indiana, and California. And you can see the reproductive numbers that we were getting from the Hawks model. California was fortunately a little bit lower. Okay, so I would say the major punchline of our work on the early time data was model selection. And this is where we use the Akaki information criteria. And this is where you can see the role of the amount of data that you have. Because the Akaki information criteria, the AIC, is going to be used to choose which model is the best. And we're going to be comparing models with different numbers of parameters, the SIR having the smallest number of parameters. We're looking at two types of data, the confirmed case counts from testing and the actual mortality. Mortality lags the confirmed cases. And of course, it's a smaller number count because certainly not everyone dies. So you might expect that with a smaller data set that the AIC might choose the model with less parameters, and that's exactly what happens. So we see that, for example, with the mortality data, it's always the SIR model, which is coming out as the optimal model based on AIC. But with the confirmed cases, which is larger data set earlier on, we see that for California, it selects SEIR, the same for Indiana, and for New York City, our AIC selected the Hawks model. And then you can see the comparison between the actual data shown as the dots and then the models, which are shown as the lines. And so the Hawks model has a variable reproductive rate. And so those are the lines that kind of change slope. And then the straight lines are the SIR and SEIR models. So that's what we get. And we have both confirmed cases and mortality cases here for the three different states. You might wonder why we picked California, New York, and Indiana. New York we had to pick because they were having the biggest outbreak in the United States. I was living in California, Elisa was in California, so we picked California, and George Moeller was in Indiana, so he ran his simulations on Indiana early on. Okay, so that's kind of a summary of early time data. So I want to move on to the next topic, which is finite size effects. So we all know that the SIR and SEIR models make a lot of sense for well-mixed populations. However, when you go into a lockdown, you control the mixing. And also, for example, in the US, we have, geographically, we're very spread out, and there's a lot of smaller cities with smaller populations. So you can't really expect that an SIR, SEIR model is necessarily going to be terribly accurate for these smaller populations. So that got us thinking about how to estimate the finite size effects. This is something that my group has worked on for other agent-based models for some things that have nothing to do with epidemics. But it was an idea that applies very nicely to epidemics as well. So this is joint work with my student Xia Li, my former student Hao Li, and Chuntian Wang, who is at the University of Alabama. She was a postdoc with us a couple of years ago. So to estimate finite size effects, we're not looking at really small populations, but maybe populations on the size of a few thousand. And so a good model for that is a Martingale formulation. So the Martingale formulation basically breaks down the model into what's effectively like a stochastic, so we start with a stochastic SIR. We start with fully stochastic agent-based model. And basically what you can do is break it down into, slides are, my buttons don't always work when I want them to. There we go. All right. So you can break it down into basically the continuum part of the model and then the martingale. So the martingale is going to capture the variability from the continuum. And you can see the classic SIR model right here, right in these G values. So that's so one can do this in a very rigorous way to take a stochastic SIR and decompose it into these two parts. And then you can start doing things like estimating variances. And the answers are not necessarily surprising with a modest knowledge of probability. But basically the variances, so you want to estimate the variances of the martingale part of the model. So this is, here we're trying to estimate the integral over time of the expectation of these variances. So we can look at both infinitesimal. So this is for the infinitesimal variances, which you can calculate. You can calculate those exactly for a specific time, but then it's a bit of a challenge to try to estimate them. You can do two things. You can do kind of an asymptotic approach to estimating them, and you can derive rigorous upper bounds. So the rigorous upper bounds we can get in terms of initial data and T. And so the takeaway here is that they all scale like 1 over n. The variances scale like 1 over n. And once you have the rigorous upper bound, you can use this directly to prove the existence of the continuum limit, to prove convergence, and the limit as n goes to infinity. So the standard, mean field limit for SIR. But these upper bounds and then the asymptotic estimates also give us an idea of what happens when we're not in the large n limit. And so that's what we're interested in. So here what we're doing is we're looking at finite sized populations, and we're looking at taking our calculation to estimate what the variance ought to look like in the mean versus the size of the population. So this is log n on the horizontal axis. And we compare simulation with the theory, and you can see these are the error bounds for different values of n. And then this is the mean line for the variance. And you can see we have quite good agreement here. So our estimate of the variance is certainly consistent with, just simulations of these kinds of behaviors for finite size populations. And so naturally what you see is that the smaller the size of the population, the more the variance is going to be important. And then we can look at realizations, right? So here's a realization. So we took a cruise ship. This is the Diamond Princess, which was one of the early places where we had, outside of Wuhan, right? Outside of China, where we had significant outbreak, and we can look at the numbers. We also looked at a small county in Nevada where they had an outbreak. So Churchill County in Nevada, that's an N of 25,000. So that's it's a slightly larger population. The Diamond Princess was roughly 3,700 people. And you can take the parameters that are estimated from the field data, and you can actually run a bunch of stochastic simulations, right? And you can see they're all over the place, right? And so here's the actual field data, and here's a lot of stochastic simulations. And what you see over here at early time is that for the stochastic simulations, there's a fair number of simulations that actually die out before having like a full epidemic. So that's another thing we see with finite size, is that not every outbreak actually leads to a full epidemic for these small populations. Diamond Princess, we can estimate, try to estimate.
Yeah. 5 minutes.
Okay, no problem. That's great. Yeah. So okay. So I think you get the general idea. So this is also some of the counties in California: San Luis Obispo, and Tehama and Ventura County. We can also try to look at the role of the finite size effects for those counties. I did want to mention a bit about networks. So I'm gonna skip these slides, and I'm gonna go on to some work that we just submitted for publication, looking at the role of the structure of networks. So I think that another thing that if you want to look at departures from SIR and SCIR models, the contact network, right, is really important. And today, in a fully connected world where everybody's on Zoom and on social network, also the distancing measures are very much influenced by opinions, right? So you can talk to your friends and they might say, well, we don't want to wear masks, and you might make a decision not to wear your mask. Or you might talk to your friends and they're all saying, oh, we have to wear masks, right? So you decide to wear yours as well. And so we looked at the influence of an information layer with its own network structure on a physical layer of actual spread of disease. So that's work with a number of our students from the summer program, with Cayenne Peng, who's one of our grad students at UCLA leading this paper. And this is joint work with Mason Porter, who's a colleague of mine in the math department at UCLA. So I don't have much time, but I'll just say that we assumed that the information layer for opinions has dynamics that's very similar to disease spread with an SIR type of dynamics, where you have both pro-physical distancing and anti-physical distancing opinions. And then we have a simple SIR physical layer where the transmission rate depends on what's happening over in the information layer. So that's it. And you can look at lots of different things. You can look at the role of these parameters. One of the things that we did was, since we were looking at the network dynamics, we looked at different network structures. And we also looked at the role of these different parameters. And so you can see here is just giving you an idea of the effect of the parameters. So for example, like the large yellow curve assumes that you have a very strong spread of information against distancing, right? And the green curve, you have a lot of suppression of contacts through, again, through the spread of information in favor of the distancing. So you can kind of see how those things work. And we also looked at the role of the network structure and the influence of the opinion on recovery rates. Those are some of the things we looked at. And so I guess the short story is that you can have lots of very complex dynamics with different kinds of issues leading to different behavior patterns. So here's an example where we looked at the role of assortativity. What is that? So assortativity is, so we looked at networks that had certain degree distribution for the connections from the nodes of the network. And assortativity tells you how much do nodes with the same degree connect to each other versus to nodes that have different degrees. That's essentially what assortativity measures. And you can see we had a couple of different examples. In fact, I think I have this on the next slide. There we go. So this example is, these are for networks with degree 2 or 8. And for this example here, the degree 2 nodes are just 40% of your network. And here they're 90% of the network. And you can see that the role of assortativity is quite different, right? Depending on which of these cases we're looking at. So now these are simple generative models for networks. We're not taking real social networks. We're taking all synthetic data to generate these plots. And they're averaged over 200 simulations. You notice that we have solid lines and we have symbols. The solid lines are actually a closure model. So we also developed a continuum, sort of a continuum limit closure model. And the way the closure models work is that you group nodes by their degree, right? So it's not like a simple SIR model. It's much more complicated set of ODEs, but it's a closed system. And so you can, why do you care? Well, you care because it's much simpler to simulate the closed system than to do the full network stochastic dynamics on a network, right? And with a closed system, there's also potential to try to do some analysis at some point in the future, although we didn't do that in this particular piece of work. Right, you can also look at the role of temporary immunity to opinions and how that affects the final size of the epidemic. right? So here we're looking at, here we're looking at what happens if you have some rate at which you go from your final opinion state back to having no opinion at all, right? And so that's a parameter tau, and so that also affects the dynamics. I have to finish, so I'll just finish with this conclusion slide that says we developed a degree pair approximation for the time evolution, that's our closure model, of the expected number of individuals in different compartments. Our pair approximation is applicable to dynamics and heterogeneous networks with specified interlayer and intralayer degree correlations. Through numerical simulations, we found that in our model, the opinion contagions can either increase or decrease the disease transmission speed, the peak infection counts, and the number of people who become infected. And learning the duration time over which people adopt opinions, whether in favor or against physical distancing, may help suppress disease transmission. Physical distancing for too short, we know this for the non-network models, simple SIR model, that physical distancing for too short a period of time may still place people at high infection risk because they're still susceptible. So I think I'm going to stop there. I have a slide with some selected references, both from my work and others' works that I found very helpful.
Thank you, Professor.
Thank you.
Thank you a lot. Are there any questions? I have one actually. Can you enter a little bit more in details about the interplay between the physical layer and the information layer?
Sure, it's very simple. Thank you. Yeah. So right. So we think about it this way. So the nodes are people. And so the people so you can think about it as a multi-layer network, meaning that you think about it this way, you have, say, so you have the same nodes on the information layer and the physical layer. It's just the way they're connected are different. So in the information layer, this could include, social media connections, right? So you could have friends on the other side of your country that you're never going to get infected from, but you talk to them about distancing. And then the physical layer is literally who you come into contact with, where you can spread the disease. So those are two networks. And so for real epidemics, certainly this layer is critical to understand, right? If you're going to have distancing measures, you expect to be going from sort of a full mixture model in a big city to something that's less than that, right? And very much has a network structure to it. We don't really have an idea of what this network looks like. I had some students in my course, for example, who took some real data. Like I had one group that took data from course enrollments at UCLA to look at what happens if students might get infected by coming to class in person and sitting in the same classroom with other students. We also looked at an example. So there is a little bit of limited data out there where people have measured physical contact, right? And there's a cell phone data set. I think it's from the Netherlands, and I think it's also students where they track their phones and they looked at who came into contact with whom. So we had that, that's a public data set. So we took that as well, but these are very limited. So we really don't know for real life how to model this, but we do have lots of kind of generative models in the network science literature that we can draw on. So that's what we did. The information layer, of course, is a different network. And again, we drew on generative models. Field data, we have maybe a little more information about possible information layer networks because there's lots of public data for social media that's available now, like Twitter, for example. So then in terms of how the dynamics work, both of these models are standard SIR models, so compartmental models. So for the information spread, we assume that everyone starts off roughly, without an opinion. But then there's you can go either in this direction or this direction, depending on who you come into contact with, right? So maybe you have some of the population that starts off with either the pro-physical distancing or the anti-physical distancing viewpoint. And then there are transmission rates, right? So you have to come into contact, but we assume that once you're in the pro-distancing group, that you can't switch. Your opinion has been solidified, so you're not going to go into the other group, right? And then you can introduce a recovery time where you might relax that opinion. You know, you're sick of social media, you don't want to listen to these people anymore, you want to just live your life, right? And then of course, this is just standard SIR, but of course it has to interact with this, right? So, you know, so it depends. So this transmission coefficient here, right? The beta it gets multiplied by an alpha, and the alpha comes from the person, whoops, sorry. The alpha comes from here, right? So you go into one of these two categories, and that's going to determine your behavior pattern, which will change your personal beta. So you could have the standard beta, you could have the larger beta, you could have the larger beta or the smaller beta. So, and then of course there's the physical recovery rate. So this is our disease, this is the information.
So it's a kind of correction coefficient on the contact matrix, right?
Yes, that's exactly what it is. Yeah, and this is not a new idea. Let me just say that, you know, this kind of idea has been studied for other kinds of disease transmission in different contexts. So we're not the first ones to look at the interaction between the information layer and the physical layer. I guess what we did was write a paper that was, we have a different closure model than the kind that has been published before. And we also have a model that's very much motivated by the COVID epidemic, right? So we're looking at those kinds of timescales.
Thank you.
Yeah, thank you.
Are there any other questions? Comments or questions? So it's quite late here in Italy.
Yeah, I'll let you go. You want to get home for your supper.
So thank you again for joining us. And
yeah, all. Thanks everybody. Appreciate your coming to
Good holidays.
Yes. There's a chat. Let's see. Oh, thank you. Thank you so much. Happy holidays. I guess you could stop the recording.
Yes. So Andrea, maybe